Welcome back. In this video, we are going to take numbers apart using a factor tree. A factor tree is a visual way to break a number into factors again and again until all of the numbers at the end are prime. Let's start with the number 108. We are going to construct 3 different factor trees for 108. Here's one possibility. 108 is 12 times 9. So we split it into a 12 and a 9. Then 12 will split into a 3 and a 4, and 4 will split into a 2 and a 2. And 9 splits into a 3 and a 3. So my prime factors are 2, 2, 3, 3, and 3. We can also write this as 2 squared times 3 cubed, or just write it as 2 times 2 times 3 times 3 times 3. A second factor tree for 108 might start differently. 108 is also 2 times 54. 54 we can split into 6 times 9. 6 is 2 times 3. And 9 is 3 times 3. So once again, I have my prime factors. 2, 2, 3, 3, 3. So this one is 2 squared times 3 cubed, or 2 times 2 times 3 times 3 times 3. Let's look at one more for 108. 108 is also 6 times 18. 6 is 2 times 3. And 18 is 3 times 6. And 6 is 2 times 3. For this one, we once again have 2, 2, 3, 3, and 3. So 2 squared times 3 cubed, or 2 times 2 times 3 times 3 times 3. So it's the same about each of these factor trees. They all ended with the exact same prime factors. But what is different? The intermediate steps are different. We grouped and decomposed the numbers into different ways. But either way, no matter how we did it in the middle, the prime factorization of 108 was 2 times 2 times 3 times 3 times 3, or 2 squared times 3 cubed. Now, let's create some different factor trees for 300. 300 is 3 times 100. 100 we can write as 10 times 10. And 10 is 2 times 5, and that's true for each of these. So, our prime factorization here, we have a 2, a 2, a 3, a 5, and a 5. So 2 times 2 times 3 times 5 times 5, or 2 squared times 3 times 5 squared. Let's look at another one for 300. We could have also written this as 6 times 50. 6 is 2 times 3, and 50 is 5 times 10. 10 is 2 times 5. I have a 2, a 3, a 5, and a 5. So 2 times 2 times 3 times 5 times 5, or 2 squared times 3 times 5 squared. Once again, the intermediate part, the middle part of the factor tree, was different for both of these, but the end result was still the same. 2 squared times 3 times 5 squared. Now we can state a major theorem, the Fundamental Theorem of Arithmetic. This theorem says that any integer that is greater than 1 can be decomposed into a product of prime factors, and this product is unique. This means that every whole number greater than 1 has one and only one prime factorization aside from the order of the factors. So even though the factor trees can look different, the final prime factorization must be the same. This is a powerful idea. It tells us that prime numbers are the building blocks of whole numbers. Just as molecules are built from atoms, composite numbers are built from primes. As teachers, factor trees can be very helpful because they make the decomposition process visible. But students should also understand that the factor tree itself is not the goal. The goal is understanding the structure of the number. It's also worth reminding students that a factor tree must end in prime numbers. If a branch ends in 6 or 10, the work is not finished yet because those numbers are composite. You are doing great. This is rich mathematics, and it connects directly to many later topics. In the next video, we will use prime factorization to find all factorizations of a number, reason about divisibility, and find factor pairs efficiently.